50% of energy is consumed by HVAC devices in buildings. And most of the times, the operational efficiencies of the systems is suboptimal. One of the primary purposes of all HVAC is to provide comfort to its occupants. So it is very important that you know how many people are present in a zone. There has been a lot of work in this area, particularly how to sense people and their associated comfort. Typically, people use PIR sensors, video cameras, or CO2 sensors, just to name a few, to detect people's presence. And comfort typically is sensed using temperature sensors as proxy, based on some standards such as ASHRAE. Of late, direct occupancy information, like the occupants directly give their feedback using smart devices, is also getting popular. Once you have the occupancy information, you can actually control the HVAC by adjusting the amount of fresh air that is required for the people present in the zone, or you can use a higher set point temperature if there are no occupants in the room. And we also have studies which are based on model-based predictive control, where people use occupancy models and zone thermal model for HVAC control, and they have shown significant improvement from the reactive approach. One point to be noted is, in all these cases, the studies are limited to a single zone, single AHU kind of configuration, or a multi-AHU or multi-VAV, and multi-zone with hard partitions. So what I mean by this? So typically in a single zone, single AHU, you have one control knob, which is AHU, and either you could control AHU supply air temperature, which is called SAT, or the AHU flow rate. People usually model temporal variations in aggregate occupancy for HVAC control, and usually do not account for intra-zone spatial variations in occupancy. And even if you somehow model this information, you cannot use this information because you have only one control knob, and essentially it will try to cool the entire space irrespective of where your occupants are present in that zone. So our focus is on large multi-AHU zones where you have multiple control knobs. As you can see, there are 4 AHUs present here, and they don't have any hard partitions, which mean air and flow can mix freely across different spatial locations. And return air temperature of any AHU depends on the set point of the other AHUs. The key distinction here being that in addition to the temporal variations in occupancy, you can also see occupancy varies significantly spatially at any point in time. You can find these kind of configurations in large office spaces, in airports, cinema halls, and malls, just to cite a few. So given such configurations, if you have a conventional control where each AHU is independently controlled based on a return air temperature sensor and a set point which is given. So based on the error between the return air and the set point, the controller tries to adjust the flow rate to meet the set point. And this is done individually for each AHU. For example, let's say you have an occupancy such as shown here, where the occupants are only in one corner of the large zone. Your conventional control, since it does not have any information or does not use any information of occupancy per control, it will try to cool the entire space. But what you ideally want is cool only the space where people are present, and maybe you can allow the other spaces to drift to a higher temperature. So given such a configuration, we wanted to see if we can centrally control the AHUs by setting a fan speed, which will be a result of a minimum energy, and at the same time it will try to maintain sufficient comfort in the spaces wherever occupancy is there. The main challenges here are how do we even model and handle the intra-zone spatial variations in your occupancy, and you should also account for the intra-zone mixing which happens across different AHU regions of influences as shown in the picture. So having described the problem, in the following slides I will explain our solution and methodology, followed by evaluations on a real-world setup, wherein I compare a reactive approach with a model-based predictive control of our own control, followed by conclusions. So our proposed control, which we call MAZIC, which stands for Multi-AHU Zone Intelligent Control, given a state S at a time t, we want to move to a state at time t plus delta t. A state is described by both temperature and the humidity. And you want to move to the next state at the expense of minimum energy, and at the same time you want to ensure the comfort is met at the next time step, which is t plus delta t. For that we use an optimizer which internally uses a zone thermal model. What I mean by this is, if you rewrite your temperature heat balance equation as a function of your mass flow rate, this is what you see. It looks a bit scary in the beginning, but it's not. I'll explain what each term means. We have an internal load term which accounts for your lighting, electrical and people load. You also have convective load, which is as a result of convection from your walls and other things due to your ambient conditions. The main term here is the intra-zone mixing, which accounts for mixing between different AHU regions of control. And we also account what is the temperature at the previous time step was. And we have the supply terms, which has both supply air temperature and the mass flow rate, which is coming inside that zone. As you can see, since there is an intrazone mixing term wherein any particular subzone's temperature is dependent on its neighboring spatial zone, there needs to be some kind of fixed point iteration to update the temperature of the current zone. So given a flow rate vector, how do you get to a new zone conditions as shown by the zone thermal model using a fixed point iteration? That's what the optimizer uses internally. The objective functions of the optimizer is to minimize the energy, which is sum of your total AHU fan power, as well as it accounts for your chiller power. We have the comfort constraints, wherein we use a people weighted temperature and a people weighted relative humidity, which are bounded. In this case, the temperature is bounded within a range of 24 to 26, and this is what typically is being used in our facilities. We also have a bounds on the mass flow rate of AHUs, which is based on your ASHRAE conditions for minimum ventilation requirements. The decision variable in the optimizer is our AHU flow rate. So given an AHU flow rate, it will try to calculate the new temperature value and then check if the temperature values actually fall within the comfort constraints. So the outcome of the optimizer will be essentially a new state which are bounded by the comfort constraint, as well as it consumes minimum amount of energy for some flow rate. And the cycle is repeated for the next time step. So in the following slide, I will explain an evaluation based on a real world setup, and I will compare both a reactive and a model based predictive approach. So for the evaluation, we have a calibrated energy plus model of one floor of a building, which is having 4 AHUs as shown in the figure, AHU 1, 2, and 3, and 4, which are on the 4 corners of the zone. Each AHU has a 20-ton capacity and has a flow rate of 11,000 CFM. The design occupancy for the floor is 200, and the occupancy hours are typically between 9 to 6 in the evening. As a standard practice, the AHUs are started half an hour before the occupancy is expected to happen. So we collected occupancy traces by deploying desktop apps at 30-minute sample, and we collected the samples across 50 weekdays and 8 weekends. And we found the peak occupancy was close to 180. And during a weekday kind of scenario, we found that the occupancy was there everywhere in the zone, which means all the AHUs were having some amount of occupancy, which means there was not much skew in the spatial occupancy. While in the weekend kind of scenario, we saw significant skew, which means only a small team comes in and they occupy one part of the large zone and then they work, and the rest of the spaces are unoccupied. As an example, a typical weekday pattern is shown here. As you can see, the occupancy across all AHU regions of influence is pretty much similar in terms of occupancy, and there is no time at which the occupancy falls to 0 in any AHU regions of control on a weekday. While on a weekend, you can see there is a significant skew and only one AHU regions is occupied, while all the other 3 are empty. Okay. So we compared our proposed control with a standard PID based control, which is being used in our facility. And we have simulated the results using different levels of occupancy information. It's a design level information, which we have 200, and the aggregate information where we know the total number of people that are going to be present in the zone, but we spatially don't know how they are distributed. And we have subzone level of information, which we actually obtained from the desktop deployed apps. So we have different cases here. One is the PID baseline, which uses design, and PID aggregate, which uses aggregate information, and SZ stands for subzone information. Okay. We simulated using a co-simulation strategy of Energy Plus with MLE Plus. So if you have a design occupancy, what the control will essentially try to do is, it will try to pull the entire space, assuming there are 200 people. For example, this is what happens in a design occupancy. Even though your occupancy might in fact be skewed, in terms of people might be present only in one corner of the room, the controller still assumes it's uniformly distributed. And again, in the aggregate occupancy, even though you know the total count that is going to be there, but you don't know how they are spatially distributed, so you again end up in pulling the entire space. While if you have a subzone kind of occupancy information and you have multiple control knobs, essentially you can cool only the spaces in which there is occupancy, and rest of the other spaces you can allow to drift, which means they can float to a higher temperature. So the results for both weekday and weekend patterns are shown here. The x-axis is the different control strategy. The primary y-axis is the energy savings, and the secondary y-axis is the percentage hours the comfort is being met. So for a weekend pattern, you see that the savings are not much, which means the occupancy is pretty much there everywhere in all AHU regions of control. So the amount of control you have in terms of energy savings is very less. In spite of that, we see about 4 to 5% savings in the energy on a typical weekday pattern. On a weekend pattern, since there is a significant skew, you can manage to get around a savings of 11% in this case. Again, if you compare it with a true baseline, which again tries to cool for all the 200 people, you see a significant savings of about 25%. But if you want to compare the proposed control with the equivalent PID based approach, then you get a savings of about 11% in this case. So far I have presented the results for a reactive based approach. Okay, and as you can see here, I'll quickly play this animation where you can see how the solution evolves with time in terms of both how the flow rate evolves, which is given by your CFM value, and the temperature in the zone also evolve. We have logically divided the entire large zone into 16 equal small subzones, wherein within each subzone the temperature and humidity are assumed to be uniform. Oops. I'll play this animation here for a weekday pattern. Yeah, you can see how the temperature evolves within that super zone. Essentially, you don't see a large variation in the temperature. The temperatures are bounded between 24 and 26, which is what our comfort constraint is. Since there is not much skew in the occupancy, all the zones have to be maintained within the comfort constraints. While in a weekend pattern, since occupancy is there only in one corner of the room, you can essentially allow the other regions to drift to a very high temperature, even as high as 30 degrees centigrade, because you have multiple control knobs. And the regions where people are present will be cooled to around 24 to 26 degrees centigrade. So we wanted to see, even if you have a perfect knowledge of future occupancy, can an MPC kind of control help? So here the x-axis is the or it has the different strategies in terms of reactive and an MPC approach, which is having a different horizon, which means the occupancy information is available at a 15 minutes, 30 minutes, 1 hour and 2 hours horizon look ahead. And again, the primary y-axis are the energy savings, and the secondary is the percentage hours comfort is being met. As you can see here, we don't get too many savings, which is the result of your MPC across both weekday and weekend patterns. And the savings are very marginal, which seems to indicate MPC kind of approach may not be really be helpful in a multi-AHU kind of scenario. So having seen that MPC is not really helpful in such configuration, we wanted to see if at all there is a case, in what cases does MPC really help. So for that we just took a hypothetical pattern which looks more like a on-off kind of pattern. Typically these kind of patterns you observe in a conference or seminar or meeting room kind of bookings, where the occupancy is very intermittent. It is occupied for only 1 hour or 2 hours kind of period in an entire day. So given such an occupancy pattern, MPC does seems to help compared with our own reactive approach. And you can see both the energy savings as well as the comfort improve with increase in the look ahead information you have. For example, at 2 hours look ahead information, you have the maximum savings of about 6%, and also you have a good comfort, which is 96%, compared to a reactive one which does not even maintain a comfort. It maintains only for 51% of the hours. So now coming to the conclusion part. So we conclude that a centralized approach in AHU control is better than individual control, and sensing occupancy at a finer level than the usual aggregate level helps, and you can save about 11% from equivalent PID based approach. And on an average, we don't see too much of improvement in using an MPC for the real world occupancy traces which we found in our own facilities. And MPC helps only when the occupancy is intermittent, where it's on-off kind of scenario like in meetings room or conference rooms, and you get a savings of about 6%. So yeah, with that I would like to conclude my talk. Open for any questions.